This video is about the method of initial rates. By the end of this video, you should understand why we can use initial rates to determine rate laws, and you should be able to use experimental data to determine the rate law for a reaction. As we saw previously, the rate of a reaction changes throughout the course of the reaction. Therefore, it's challenging to determine the rate at any particular point in a reaction. Recall too that reactions are reversible. This means that as soon as the forward reaction has proceeded by a certain amount, the reverse reaction will begin to become significant. This is problematic when we're trying to determine rate calculations, since we're trying to relate our rate to our concentration of reactant. Since the reverse reaction is also occurring, the concentration of reactant doesn't simply decrease over time. However, if we choose conditions when the reverse reaction can be neglected, we can determine the rate based on the concentration of reactant only. This is where the method of initial rates come in. At the very start of a reaction, just as it's getting going, we know that there isn't significant reverse reaction. Therefore, the relationship between concentration of reactant and reaction rate is a reliable relationship. The initial rate of the reaction is the instantaneous rate determined just after the reaction begins. This eliminates the effects of the reverse reaction since there's no time for the reverse reaction to really get going. In the method of initial rates, we run experiments several times with different concentrations of reactants, and we measure the initial rate of the reaction. Using this data, we can determine what effect the concentration of the reactant has on the initial rate. In other words, if we look at two trials between which we double the reactant concentration, what will this do to the rate? Will the rate double, meaning it's first order, quadruple, meaning it's second order, or remain the same, meaning it's zero order? The best way to understand this method is by looking at some examples. In our first example, we have the equation written here. We start by writing the general form of the rate law. Our only reactant is N2O5, so our general form of the rate law is rate is equal to the rate constant times the concentration of N2O5 raised to some power. We need experimental data in order to determine values for K and M. Let's take a look at this data. We have a very simple set of data here with only two trials, just to simplify this example. You'll notice just by looking that we've halved the concentration of N2O5 between trial 1 and trial 2. Also by inspection, you can probably figure out that we've also halved the rate of the reaction. Therefore, we know that there's a proportional relationship between the concentration of N2O5 and the rate. When we halved N2O5, the rate was cut in half. This means that the value of M is 1. This reaction is first order in N2O5 since the concentration of reactant is directly proportional to the rate. In some cases, the values might not be as straightforward, so let's look at a mathematical approach to this same problem. Again, here's our experimental data. We can write the rate law for rate 2 divided by the rate law for rate 1. Then we can plug in rate values and concentration values. K will cancel since it will be the same on the top and bottom. This allows us to solve for the value of M. I've just algebraically substituted in, and I can determine that the value of M is 1. You probably didn't need to do this here since you could just tell by inspection of the data, but this is a handy method if the data isn't quite as obvious. So in review, if we compare trial 2 to trial 1, since the rate doubled from trial 2 to trial 1, as did the concentration, we know the rate law must be rate is equal to the rate constant times the concentration of N2O5 raised to the first power. Here you can write the 1 or not. It's the same thing in either case. It's just the exponent 1. We would say that this reaction is first order in N2O5. Now let's look at a more complicated example. Since we have 3 reactants, it's necessary to run several trials in order to isolate the effect of each individual reactant on the rate. Again, let's start by writing the general form of the rate law. In this case, 3 reactants will be included in our rate law. Now we need to use experimental data to determine the values of N, M, and P, our orders of our reaction. In order to do this, we need to consider each reactant individually. And for each reactant, we need to essentially run a controlled experiment. In other words, we need to find two trials in which we varied the concentration of the reactant we're interested in, but held the other concentrations constant. This will allow us to determine the relationship between each reactant and the rate individually. So take a look at the data and find two trials in which BrO3- has changed, but Br- and H+ has remained the same. You'll see that in the first two trials, that's true. From trial 1 to trial 2, we've doubled our concentration of BrO3-, and you'll also see that our rate has doubled. This means that this reaction is first order with respect to BrO3-. Pause the video here and try to determine the orders for Br- and H+ using this same method. When you come back, I'll reveal the answer. Welcome back. We previously said that this reaction was first order in BrO3-. You should also have determined that it's first order in Br- and second order in H+. To determine the overall order of this reaction, we add up each individual order to give us an overall order of 4. Here's an example from a previous AP exam. Pause the video here and try to answer these questions. When you come back, I'll reveal the answers. Welcome back. Here's the answers. Since the concentration of B doubles between trial 2 and trial 3, and the rate also doubles, we know that the reaction is first order in B. Determining the order for A was a little trickier since there weren't two trials in which A was varied and B was controlled. However, if you look at trials 1 and 2, you'll see that B doubled and the rate doubled. Therefore, we know that the reaction must be zero order in A, since B was responsible for the rate doubling, and the change in A must have done nothing. From there, we can plug values from any trial into our rate law, which we've done here, to solve for the value of K. As you've seen before, then we can use algebra to solve for the unit on K. In this case, it's 1 over seconds, or seconds to the negative 1. From there, we can use the rate law to answer questions C and D by plugging in values. That brings us to the end of this video. Let's review our goals. First, we looked at why we can use the method of initial rates to determine rate laws. This is because at this point the reverse reaction is negligible. And then we looked at how to use experimental data to determine the rate law for a reaction.